Hello, everybody, and welcome back to 4-H. How are computers even possible? This episode, 4-H computers logic. All you need is NAND. So last week, if you recall, we built a NAND gate out of just transistors, just a couple of transistors and some wires and then some resistors. But we don't talk about resistors. Um, but why do we do that? Well, let's remember at the beginning of the class, we talked about what do computers actually have to do to run computer programs. And we listed 7 things that form the mnemonic acronym cluster, right? We got to choose, listen, understand, sequence, talk, evaluate, and remember. Well, from last week's project, um, you may have noticed that we built something that could listen and talk in a certain way. So pause the video if you can figure out how our little project from last week was able to listen and talk. What parts of the project were listening or talking? Okay, if you've had enough time to think about it, the buttons, the switch buttons were how our circuit listened, and the lights were how it talked, right? Because listening and talking means communicating with the outside world, and that's how we did it. Um, those are the easiest things to talk about with regard to computers. There are lots of ways that computers can talk and listen, as we talked about in the first episode. But today, we're going to start talking about choosing, which is for the first real step towards a thinking computer that can really be a robot assistant. Um, so with that, we move on to wires are information, part one, logic. So let's imagine that a wire is true if it is high voltage, and false if it is low. As we said in the first episode, there are many different ways to describe a high voltage wire. It's cold, it's hot, it's on, it's 1, it's 5 volts, whatever. Similarly, there's a lot of ways to describe a low wire, ground, off, false. But today we're going to talk about true and false because we're talking about logic. And the cool thing about this is that we can use transistors to answer questions about our wires. Questions are functions. They take an input, they produce an output. Now, how many different functions can you make with one input wire? Well, functions produce an output for every possible input value. So in the case of a single wire, wire A, the function must produce a result when A is true and a result when A is false. So how many different ways do you think there are to produce a result for both of these inputs? Pause the video if you want to think about it before I tell you. Okay, well, the answer is 4 because for each value of the input, you have to choose which output to make. So, for instance, if A is true and you return true, and A is false, and you still return true if A is false, that's a function. It's not a very interesting function. It's the always true function, but it's still a function. Um, if you return true when A is true and false when A is false, then you're basically the A function, the function that just basically that just repeats what the input wire is. If you return false when A is true and false when A is false, you're the always false function. And if you return true only when A is false, then you're the not A function. We put a bar over the top of A to signify that we mean not A. So the answer is 4. There are 4 ways to make a function out of a single input wire. Now, how many different functions do you think we can make with 2 input wires? For instance, A and B is a function of 2 input wires. It returns true only if A is true and B is true. Otherwise, it returns false. How many different functions do you think we could make? Well, first of all, the inputs now have four different possibilities, right? Because A can be true or false, and B can be true or false. And so each input is a combination of these two wires, right? So pause the video if you can, and think, see if you can figure out how many different functions we can make from these inputs. Okay, well, the correct answer is 16, which might not be obvious, but if you think about it, each function has to make a choice for each one of these four boxes, right? And there are two choices for each box, true or false. The function can return true or the function can return false. So the number of possible functions is the number of different combinations of these boxes. So you make it one choice here, that's two, times another choice, two, times another choice of two, times another choice of two. So there are 16 different possible outcomes here. Some of them are very boring, like the always true function if every box had a true in it. Or, for instance, the A function, which just has a true here and here when A is true, and a false here and here, and it doesn't care at all what about B. So there are some functions that aren't very interesting, but there are several that are very interesting of these 16. For instance, the AND function. Um, that's true only when A is true and B is true. And this is the symbol we use for the AND gate. We call the function chips gates. Not sure where that comes from, but it's a nice short word to use for sort of a functional unit. So this is the AND gate. This is the not A function. Okay, so it's false, as you can see, whenever A is true, but it's true whenever A is false. And we use this little symbol here to indicate that. And this little ball on the end takes anything before it and flips it, makes it it's the little not ball. And another way to write the not A function with text is to put A with a bar over it, as we did earlier. So that's not A. Or, okay, um, A or B is true unless both A and B are false, right? I mean, if either one of them is true, then A or B is true. So it's only false here in the corner when B is false and A is false. And we use a little symbol like this to indicate or. If you look online, you'll see a more curved version of this shape, but Google Docs doesn't have that, at least in the version I have. So we'll make do with this little chevron thing here. Okay, now this one's interesting. This is called NAND. This is the thing you made last week. Now this is true whenever and is false, right? Because that's what this little dot after the and symbol means, right? So it's not A and B. So if A and B is true, in other words, A is true and B is true, NAND returns false. Otherwise, it returns true. It's exactly the opposite of and. And finally, just one more interesting one I want to show you is exclusive or. When you see an X in the front, it means exclusive. Um, this means the X basically means yeah, but only one of. Okay, so it's just like A or B, except the X means that only one of them can be true and not both. Okay, so as you can see, if it were or, this box would also be true, right? Because it would be true as long as any of them are true. Well, XOR means exactly one of them has to be true. So if B is true, sorry, if B is true, then A has to be false. And if A is true, then B has to be false. Otherwise, it's false. You'll see this come up for various reasons in computers. It's a very handy operation to have, even if it's not something that we humans find very useful in our daily language. But here's the secret, okay? Here's the big surprise. This is why we built NAND gate last time. you can build all of these binary gates. You can build all 16 functions using just NANDs, okay? Why does that matter? Well, we built a NAND last week using just transistors. And as we said at the beginning of the class, we're going to level up each week, starting with one simple tool, and we're going to make everything else out of that, which is really amazing given how complicated computers appear to be. Yes, you can build any question about two wires using just transistors. And this extends to 3 wires, 4 wires, 5 wires. Any combination of wires, you can make any function you want with transistors just by combining the binary gates that you've already made. For example, this circuit produces A or B using only NAND gates. Now, an interesting question is why? This is a NAND, and these, well, what are these? What are we actually NANDing here at the end? Well, this NAND gate is actually NANDing A with itself. The A wire splits up and goes into both inputs of the NAND gate. Okay, so we're saying A NAND A. But if A is true, then A is true, right? And if A is false, then A is false. So the only way A and A can be true is if A is true. So the only way NAND A and B, A and A can be true is if A is false. So basically, this trick here is just doing a not. It's true if not A is true, and it's false if A is true. We're just splitting up the A wire and saying, well, they can't both be true, which means A can't be true. And they're doing the same thing down here. So really what this function is producing is, here's the not A that we talked about coming out of here. And here's the not B that we talked about coming out of here. And then we're NANDing not A, not B. But why does that produce A or B? So this is a cute little puzzle. You might want to think about it. So if you do want to solve it before I explain it, then pause the video right now and I'll wait for a few seconds. Okay, well, there's this rule that was invented a while back called Demogorgon's rule. I'm going to call it Demogorgon's rule. It's, that's kind of cool. Maybe it's not actually called that, but it's close. It turns out that not A or B is equivalent to not A and not B. And similarly, NAND, that is to say, not A and B, is equivalent to not A or not B. Okay. And let's talk about why. So if you think about it, when is A and B false? Well, it's false when they're not both true. But that's the same as saying, well, one of them has to be false, right? Because if neither of them is false, then the whole thing must be true. So that's why it's equivalent to not A or not B. This is another way of just saying one of them has to be false, right? Not A or not B. They can't both be true. This is just not both of them, right? If they're not both true, then one of them must be false. That's all that's saying. Similarly, up here, this is basically saying neither, right? Not A or B. So neither of them is true. Well, that's the same thing as saying the first one isn't true and the second one isn't true, right? So these are actually kind of obvious if you think about it in English for a little while, but very useful in circuit design. Now, if we go back to here, we realize that this function is just NAND of not A and not B. But looking at here, we already have a NAND here. the NAND is not A or not B. If so in the previous example, this not A becomes not A, which is just A, and not B becomes B, right? So so NAND of not A and not B is just A or B. It's a little tricky, but think about it, get your head around it. You can convince yourself of it. Conclusion: you can answer any logic question about two wires using only the lowly transistor, just this tiny little device that lets you disconnect one wire with another wire. Again, that's the only tool we're using. And that's all we've got for this video. In the next video, I'm going to talk a little bit about um, our next device that we're going to use, which is the integrated circuit or chip. It is a way of not having to put a ton of tiny little wires in your breadboard anymore once you've already built something. And you'll see what I mean shortly.